This AP Calculus example is starting us with a function's derivative here. So we're being given the derivative to start on this problem. And then they want to know at which of the following x values does f have a point of inflection, an inflection point. So what does it mean for something to have an inflection point? Well, in order to be an inflection point, your point has to fit two things. First and foremost, the second derivative at that value needs to equal 0, or the second derivative at that value is undefined. So that's the first thing you would be looking for. And then the second thing that most people forget about is it's not enough just to do that. It also needs to change concavity at that point. So it needs to change from being concave up to concave down, or concave down to concave up. You have to have a change in concavity. If it doesn't change concavity, it's not an inflection point. So to do this, what you want to do here is anytime somebody wants us to find an inflection point, this is really asking us to perform a second derivative test. And so step one of the second derivative test, guess what? Find the second derivative. Conveniently, they started us with the first derivative, so we don't have to take two derivatives. We just need to find the derivative of our derivative. So finding our second derivative here, this would be following the power rule. I bring my power down, so that would be 3x, subtract 1 from the power would get me x squared. And then doing the same thing here, bringing the power down, minus 4, subtract 1 from the power would get me x to the 0 technically, but anything to the 0 power is just 1, so we don't need that. Then step 2 of the process, this is where we check and find these starting points to look at. So we want to know, when does this equal 0? When does our second derivative equal 0? We don't have any fractions here, which is usually when you'd be looking out for the undefined situation where you would run into division by 0. So luckily for us, we don't have to worry about this portion of the second derivative test on this one. From there, you would go ahead and solve the algebra problem to see what our x's are. So add 4, we get 4 equals 3x squared, and then we would divide by 3, you get 4 over 3 equals x squared. And now we would go ahead and square root both sides of this. So square rooting both sides of this. Remember, when you apply the square root, you get the plus minus version of this. So this would be plus or minus the square root of 4 over 3 equals x. So out of here right now, what we really have are two options. We've got negative 4, root 4 over 3. That's one option. And then we've got the positive version of 4 over 3, root 4 over 3. Here we could clean these up a little bit before we move on, just to help ourselves see a little bit more what's happening here. This would be negative, and when you've got square roots, you can split up the top and the bottom into their own root. And so you can see on the top there, the square root of 4 would just be 2. So we've got negative 2 over root 3, and then down here we could do the same thing, split up the top and the bottom, and so out of there we end up with 2 over root 3. So these are now our possible inflection points. So step 3 of our process is we would come through and you would do what's called the second, this is where this second derivative test happens. We would do the second D test. That is just this number line game that you play. So we would lay out our number line and mark those possible inflection points. And so we would say, okay, I've got one possible inflection point is at negative 2 over root 3. Then I've got another possible inflection point happening at 2 over root 3. And from here, we want to go ahead and choose test values from each of these regions. So I need a test value for each of these spaces right here. So negative 2 over root 3, when you do stuff like this, you got to say to yourself, how do I even know what that is? I don't have a calculator right now. Well, remember, root 3 is going to be just slightly smaller than root 4, which you actually know, right? So you know the square root of 3 has to be less than 2. And so what you can say here is that this is going to be a little bit bigger than negative 1. So maybe I push this out, and you don't have to be exact, so any value over here will work. So I know negative 10 for sure would work as a test value here. In the middle of these two things, well, one's negative, one's positive, so that means in the middle of those, I know for sure 0 is there. And the same idea that I used to pick negative 10, I'm going to choose positive 10 outside here. So now remember, we are doing a second derivative test. And so that means that we are going to test everything in the second derivative. Remember, math people are not creative namers. If it's called the second derivative test, it's because that's what you're doing. So we're going to take and we're going to plug negative 10 into our second derivative. We're going to take and plug 0 into our second derivative. And then we're going to take and plug negative 10 into our second derivative. So our second derivative we found back on step 1. Plugging in negative 10, I get 3, and instead of x, I plug in negative 10 minus 4. So this would be 3 times 100. So we get 300 minus 4 is going to give us 296. And the beautiful thing about this, that's why you choose a number like 10, is the math is easy, and you only care about positives or negatives coming out of here. So we got a positive 296 coming out of there. So then that tells us that our graph is concave up in that section. And now we come and do this, plug in the 0, so we get 3 times 0 squared minus 4. That's going to equal 0 minus 4. That's going to give us negative 4. And so we know that this is negative and therefore concave down in that section. And then we'll do our last little point. We'll do our, not negative 10 on this side. This is our positive 10 for this test value here. So this would be 3 times 10 squared minus 4. And so out of there, we end up getting out, again, 300 minus 4 gets us 296. So this is positive and therefore concave up. So now we want to check, are these things changing concavity? Well, at our first inflection point here, it's going on the left side, it's concave up. On the right side, it's concave down. So yes, that is an inflection point. It fit all of our criteria. The second derivative equaled 0 there, and it changed concavity. And we look at our other inflection points, and we'd say, oh, it's going from negative to positive, concave down into concave up. So that is also fitting our requirement that it has to change concavity. So this is also an inflection point. So now we know that both of our possible inflection points were actual inflection points, and now we go looking for our answer. And in our answers, we'll see that the only answer available to us is this answer here. Notice that it doesn't say what are all the inflection points, right? Be careful on these questions. They're not asking you for all the inflection points. They just wanted to know for which of this list of x values that they gave us to work from, which of those x values is an inflection point. Well, we found negative 2 over root 3 is an inflection point, and positive 2 over root 3 is an inflection point. However, the only one listed is the negative one, and so that's the only answer on this question. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.